We often take for granted that planets orbit around the Sun, and that the reason why they do this is due to the force of gravity. But this alone doesn't explain why orbits have the shape that they do, where we notice that at one point in the planet's year it can be closer to the Sun, and that at other points in the year it can be further away from the Sun, in what, mathematically speaking, we would call an elliptical orbit. Now, hundreds of years ago, a very smart chap by the name of Kepler first noticed that planetary orbits are ellipses. But the question is, why? Well, today, I'm going to use the laws of physics as formulated by Sir Isaac Newton to show you why planetary orbits must be ellipses. The question of how planets move around a star has become increasingly relevant in recent years with all of the discoveries of extrasolar planets. So where better to start if we want to understand the dynamics of how planets move around a star than by looking at how the planets move within our own solar system. So the first real major attempt in order to actually tackle this in a way which seems to match quite nicely with reality was by the German astronomer Johannes Kepler in the 17th century. So the story goes that Kepler had access to a huge wealth of very precise astronomical measurements taken by the late astronomer Tycho Brahe. And from these measurements, Kepler was able to spot a number of patterns, and within these patterns he was able to tease out what later became known as his 3 laws of planetary motion. So they can be summarized broadly by the first law being that planets orbit in ellipses. And there's the added statement that the Sun in this elliptical system is at one of the focuses of the ellipse. And I'll show you actually what this means just on the next slide after we've just stated what the laws is, so hold with me just for a moment. The second law that he deduced is that, let's say for instance, here you have the Sun, and here you have a planet. Draw a line between the Sun and the planet, and then wait a certain amount of time, and the planet will say move like this, and then draw another line between the Sun and where the planet now is. And if you shade in that area, then wait until the planet is at a different point in its orbit, say over here. Again, draw a line between the star and the planet. Now wait the same amount of time for the planet to get into its second position as you waited this time around. Draw the line again, shade in the area, and if you compare the two areas for these two different arc lengths within the orbit, you find that if you call this maybe A1 and you call this area A2, then the second law can be summarized as saying that A1 is equal A2, or just alternatively that planets, well, we would say that the radius vector of the planet sweeps out equal areas in equal times. And this law may not seem that impressive at first glance. There is actually some really hidden physics inside of there, which I'll be illuminating in my next video. And finally, the third law, which is incredibly useful, and I use it all the time just in my own research in exoplanets, is that the total amount of time it takes for a planet to go around a star, known as the orbital period, P, if you square that, you find that it is directly proportional to the semi-major axis of the orbit cubed. Now, the semi-major axis, basically you can think of it as how far away the planet is from the star, and in fact it's exactly that in the case of a circular orbit, but I'll show you precisely how to work it out in just a moment. Now, the first two laws were deduced quite early on by Kepler, actually in 1609 originally, whilst the third law, which took a little bit more effort to deduce, he figured out in 1618. But these were just empirical laws. He'd spotted the evidence for them amongst the data, but he didn't know why these laws were true. And an explanation of why they're true actually would have to wait for Sir Isaac Newton to come along. Now what I'm going to do in the rest of this video is I'm going to hone in on the first law of planetary motion. Firstly, I'll explain what it actually means by showing you what an ellipse is and say how we can describe the orbits of planets. And then for more advanced people interested in knowing why planets orbit in ellipses, I will then go through and present a modern version of Sir Isaac Newton's original deduction, his original mathematical proof that planets orbit in ellipses due to his law of gravity. So at the end of the day, an ellipse is just a fancy word for an oval, which many of us will already be familiar with just from day-to-day life. We can describe the shape of an ellipse by drawing two lines across it, one from the two furthest ends, and then one line intersecting the two closest parts. And in the case of a circle, these two would just be absolutely the same, because in a circle you are always a constant distance away from the centre. But in the case of an ellipse, we call this longest axis the major axis, and the shortest one, predictably, the minor axis. And the distance halfway across the major axis is called the semi-major axis, denoted by the letter A conventionally, whilst the distance halfway across the minor axis is conventionally denoted by B, which is the semi-minor axis. So when Kepler said that planets orbit in ellipses with the Sun at one of the foci, what he means, if we draw on this diagram, is let's say you have a star here which lies along the major axis, but it's not quite in the middle of the major axis. It's actually displaced from the middle by a distance A times by some number which is between 0 and 1. So if this number E was just 0, then the Sun would be at the centre, and if it was 1, then the Sun would be touching the outside edge of the ellipse. And then the planet, it could be the Earth, it could be Jupiter, it could be Mars, then travels along this green line, and that is what the orbit of the planet looks like. So we can draw a line between the Sun and the planet and call this R, and that's just the distance between the Sun and the planet as a function of time. And we can also, if we want to describe it mathematically speaking, define an angle theta between the major axis and the radial vector. So for instance, when this angle theta is equal to 0 degrees, the planet will be at its closest approach to the Sun. And we call this point of closest approach the periapse. And when this angle theta is equal to 180 degrees, when the planet is over here, it will be at the furthest distance away from the Sun. And we call this point the apoapse. And we can figure out expressions for how far away the planet is from the Sun at the periapse and the apoapse just by looking at the geometry in this case. So for instance, when it's at the periapse, the distance will just be this line here, and let's call it RP for R at periapse. And so we can see that from the centre of the ellipse to the outside edge here, by definition, is just A. And then if we subtract A times by E, this little bit of distance here, we'll then get what RP is. So RP is just A minus AE, which we can simplify as A times by 1 minus E. And similarly, for the apoapse, the distance is just going to be, so when the planet is here, our apoapse will be this distance, and so it's just going to be A plus this small A times by E. And again, we can simplify that by taking out a factor of A, and we get A1 plus E. So this gives you the minimum distance of a planet from the Sun, and this here gives you the maximum distance. in terms of the quantity A, the semi-major axis, and the quantity E, which is called the eccentricity. It tells you basically how much the orbit deviates from being a circle. So this here is just the eccentricity. So notice from these two expressions that if the eccentricity is equal to 0, then the minimum distance and the maximum distance are both just equal to A, which is what defines a circular orbit, where you're always at a constant distance away from the star in question. So for ellipses, the quantity E, the eccentricity, can vary between 0 and 1, where if it's 0, you have a circular orbit, and in the case of it approaching 1, then actually the planet would then be unbound and it would be able to escape from the sun. So some comets, for instance, can have an eccentricity which exceeds 1. So now let's turn to ask why planets orbit in ellipses. And to do this, we need to understand how gravity works. And you can explain why planets orbit in ellipses in the framework of Newtonian gravity as formulated by Sir Isaac Newton in his Principia Mathematica in 1687. And what's really significant about this is that by unifying the laws of how everyday objects move here on the Earth with how the planets and the moons were orbiting up in the heavens, Isaac Newton showed that the laws of physics are universal. So this is a very neat and very historically relevant trick that I'm going to show you here of how to prove Kepler's laws. So what is his law of gravity? How does gravity work, at least according to Newton? So what he stated is that, let's say you take two objects, each of which contains atoms, and so they have mass. Newton stated that these two objects attract each other due to gravity. There's no repulsive gravity, and that the force of gravity depends on how much stuff there is in each of the objects. So say if I double the amount of stuff in this object, the force of gravity will double. He also stated that if you take the two objects and move them 2 times closer, then the force of gravity becomes 4 times stronger. So we say that gravity follows an inverse square law. So both these observations can be summarized, mathematically speaking, by the force being proportional to the product of the two masses, m1 and m2, and that also the force is inversely proportional to the distance between the objects squared. And you can combine these two observations together in that the force will be equal to some constant of proportionality. It's just a number. Here it's called Newton's constant of universal gravitation. So it's 6.67 times by 10 to the minus 11, if you want its actual value, times by the product of the masses, divide by the distance between them squared. And this deceptively simple expression describes how the force of gravity depends both on mass and on distance. And it's relevant whether you're measuring the force of gravity, say, between myself and, I don't know, the books behind me, or between the Earth and the Moon, for instance. It's a universal law. So this is the first ingredient we need in order to do this proof. There's just one other ingredient we need, which is one of Newton's 3 laws of motion. It's that if you exert a force F on an object, then the relation between the force and the acceleration it feels is just given by the force is equal to the mass times by the acceleration. F equals ma, which is just Newton's second law of motion. And these two results, the one in the circle and the one in the square, are all we need in order to prove Kepler's laws, which is quite nice. Now the proof does get a little bit involved though, so in order to do this, efficiently speaking, I will need a little bit of calculus and some vectors. If you're not familiar with those, then feel free to drop me a message down below and I'm happy to recommend materials so that you can learn how this all works. It is worth noting though that in Newton's original proof, he didn't actually use calculus because he'd only recently invented it. But he used a very convoluted geometric proof, which is actually even harder to understand than using calculus. And so hence why I'm going to go through this more modern proof. So to prove Kepler's first law of planetary motion, what we want to solve is a classical problem in orbital mechanics called the two-body problem. It's just basically how do two gravitating objects move as a function of time. So to set this up, let's imagine we have the Sun, which is over here for instance, and over here we will have a planet. The Sun will have a mass, let's call it m star, and the planet will have a mass mp for mass of the planet. We can define some reference origin that we'll use to define all our coordinates from, and in this coordinate system the distance between the origin and the Sun will be a vector that we will call r1, and the distance from the origin to the planet we're similarly going to call r2. And these are vector quantities, meaning that they have a magnitude and a direction. And equally, the distance between the Sun and the planet we can also draw, and we're just going to call this distance r. Now, due to gravity, the planet is going to experience a force pulling it towards the star, which will be directed in this direction. So let's call this F2. And equally, due to the gravity of the planet, the star will also experience an attractive force that we shall call F1. Now, we can use our first key ingredient, which is Newton's law of universal gravitation, to figure out what F1 and F2 are going to be, because he tells us that the force of gravity between two objects, its magnitude is just given by g times by the product of the masses, in this case m star times by mp, divided by the distance between them r squared, and the direction will be along the direction of the vector r between the two bodies. So if we make f a vector, then we have to include a vector of length 1 in the direction between them, which is a unit vector. So this little hat up here just means a vector in the direction between the planet and the star with total length 1. So for instance, the vector r is just given by the length of the vector r, which is just a scalar, it's a number like say 5 meters or 5 million kilometers, times by the unit vector. So the unit vector say would be like that, and when you multiply by the distance between them r, you get the total vector between them. Okay, so this is how we can measure the force between them. And notice though that F1 is in the opposite direction to F2. They're of the same magnitude because it's a mutually attractive force, but this is actually a manifestation of Newton's third law, which tells us that F2 is equal to minus F1, just because they're directed in opposite directions. Great. So now we can use our second key ingredient, which is Newton's second law of motion, or just F is equal ma. And we can use this to figure out the acceleration on the two bodies from the force of gravity acting on them. So the acceleration is given in reference to the origin point, which I'll call O here for instance. So the force on the first object, this star, will just be given by the mass of the star times by the acceleration it's experiencing. And we'll have the same for the planet. F2 will equal the mass of the planet times by its acceleration. Now, how do we get the acceleration? So the definition of acceleration, as always, is just the rate of change of velocity, which we can write as dv by dt, the time derivative of velocity. And then remember that velocity is just the time derivative of position. So a1, for instance, is the derivative of v1, which will just be the second derivative of r1, because v1 is dr1 by dt. So we can substitute this relationship into here in order to write this as m star times by d2r1 by dt squared, and this is still a vector. And similarly for the force on the planet, we have the mass of the planet times by d2r2 over dt squared. And then the question is, how does this help us? Well, the really key trick to note is that just from this diagram, which we have here, we can see that if you start here and want to travel from the star to the planet along the vector r, you can also go against the vector r1 and then add the vector r2, or otherwise speaking, the vector r is exactly equivalent to r2 minus r1. And so if we take the second derivative of both sides of this expression with respect to time, then you can start to see here that we can find a way in order to use these two results down here in order to get an expression involving the distance between the planet and the star. Okay, so bear with me for just one moment, because we also know the expression for F1 from up here, so we can write that this here is just equal to g times by the mass of the star times by the mass of the planet divided by r squared in the direction of r. And this is exactly the same, just with the aforementioned minus sign from Newton's third law. Mass of the star, mass of the planet over r squared in the r direction. Right, okay, so now what we want to do, now that we have these two expressions, is that if we take this and substitute it into this expression at the top, and do the same using this value of d2r by dt squared up here, then we can figure out what d2r vector between the star and the planet divided by dt squared is equal to. So let's do that on the next page. Right, so here are our two expressions for the force on the planet and the force on the star. But what we want is an equation describing the time evolution of the distance between the planet and the star. So remember that we had that the second derivative of the distance vector between the planet and the star is just given by the second derivative of the distance vector from the origin to the planet minus the second derivative with respect to time of the distance vector between the star and the origin. And notice that we've almost got these two from these two equations up here, which I can call equation 1 and equation 2. All we need to do to get d2r1 by dt squared is just cancel this m star here and here, and for d2r2 by dt squared, just cancel the mp here and the mp here. Then all we need to do to get this is just take equation 2 and then subtract equation 1 from it, which will then tell us that d2r by dt squared will just be given by minus g times by the mass of the star divided by r squared in the r direction from equation 2 minus g times by the mass of the planet divided by r squared in also the r direction. And so if we take these two quantities and bring them over to the left-hand side, we can get our differential equation that we want to solve, that d2r vector by dt squared plus g times by the sum of the mass of the planet plus the mass of the star divided by r squared multiplied by the unit vector in the r direction is equal to 0. And this is the equation that we need to solve if we want to figure out the time evolution of the distance vector between the planet and the star. So let's go on and solve it. In order to get a handle on what this equation is actually telling us about how the planet will orbit around the star, we can use something called the cross product that you might have encountered before in your studies of vectors. But for a brief reminder, if we have two vectors, say A and B, the cross product of those two vectors is just defined as the magnitude or length of the vector A times by the magnitude of B times by the sine of the angle theta between them. So say if A was here and B was here, this would be the angle theta, and the cross product of two vectors spits out a vector as well, which is directed at 90 degrees to both the vector A and B. So this is a unit vector traditionally denoted by n because it's normal to both A and B. Right, so how are we going to use this result here? Well, if we look at the equation that we're interested in, right up here, here's an idea. Why don't we take the vector r and cross it with this entire equation, like this? R crossed with all of this. That would be what you would get on the left-hand side, whilst on the right-hand side, you have r crossed with 0, and 0 times by anything always gives 0. So we have r cross all of this up here, and we can break this apart term by term, because we have two terms which we're summing here, and so we can take the cross product with each of them in turn. So let's see what we'll get. The first term gives us r cross d2r by dt squared. We then add the second term. If I take out the constant out the front, we have g times by the mass of the star plus the mass of the planet divided by r squared, just a number, so I can take it out the front. Then we have r crossed with r unit vector, and all of this is equal to 0. But from the definition of the cross product here, if we do r, which is just directed in the direction of r, and then cross it with a vector in the same direction, then the angle theta would actually be 0. And so the cross product of any two vectors in the same direction always gives 0. So this is just going to be 0, and this term will die. And hence, what we're learning is that the vector r crossed with d2r by dt squared must equal the right-hand side, which is just 0. Now we can extract slightly more information from this equation by noting that this equation is exactly equivalent to the time derivative of the vector r crossed with dr by dt. So this is just one time derivative here. You can check this just by differentiating it term by term via the product rule. The first term would give you dr by dt cross dr by dt, which would give you 0, and the second term from differentiating this then returns this expression. And so this must equal 0. And remember that if you ever have an expression of the form, say, df by, say, dt is equal to 0, then by integrating this expression, it tells you that f must equal a constant, because when you differentiate a constant, you get 0. So what this expression tells us is that the cross product of the vector r and the single time derivative of the vector r must equal a constant, and because the cross product always gives you a vector, it must be a constant vector, which we'll denote by h. So the conclusion from doing this is that r crossed with dr by dt is equal a constant vector h. As it will turn out, and we'll see shortly, this is actually the angular momentum per unit mass, but I'll be showing why that's true later. But let's examine now the physical content of this nice simple equation we've deduced, which actually tells us a lot about how planets are going to orbit. So what does this equation mean? Well, the key is buried in the fact that this vector h is a constant vector. And because it's defined in terms of the cross product, it must be at right angles to both the vector r between the planet and the star and dr by dt, which you can think of just as a velocity. So if we draw what this looks like, we'll have the star will be here, we have the vector r, and then the planet is living out here. We'll have the velocity, which at some time maybe say it's like this, for instance. So this is the direction that r is changing. The planet is then moving along, let's say like this. And now the vector h is perpendicular to both these two vectors. So it will actually be sticking outwards like this. So it's at a right angle to both of these. And the key is because the vector h is constant, meaning it has a constant direction and a constant magnitude, this actually defines a plane in three-dimensional space. Because if h was not a constant, say it was rotating, then the plane would be rotating. But because h is constant, it forces r and the derivative of r to lie within a plane. So we've deduced one key result already, in that planets orbit in a plane. And this is good because it means that we can reduce this three-dimensional vector problem that we have just to a two-dimensional problem defined inside of this individual plane. And to do this, we're now going to introduce plane polar coordinates within this two-dimensional plane. So let's orient ourselves such that we're looking down along the vector h, looking down on the plane that the planet is orbiting about the star in. So what we'll see is the star, say here, and the planet just over here. And we'll describe this system not in terms of x coordinates and y coordinates, but in terms of the distance r between the planet and the star and the angle theta that it makes to some reference direction. We can, though, figure out the relation between the traditional x and y coordinate system and this polar coordinate system by noting just from trigonometry that the distance in the x direction is r times by the cosine of theta, and the distance in the y direction is just r times by the sine of theta. So we can write the vector r between here and here in column vector notation as just being r times by cosine of theta for the x component and r times by sine of theta for the y component. We can then peel out a factor of r, the magnitude of this vector, and we just get r times by cosine of theta, sine of theta. But remember that r is just given by the magnitude or the length of the vector times by a unit vector in that direction. So we've actually figured out here an expression for the unit vector in the r direction. Now, the planet is going to live somewhere within this plane, following some orbit that we don't know the shape of yet. But if we want to define a two-dimensional coordinate system, we also need to define a direction at right angles to this vector r, so that we have well-defined coordinates. So we can also define a unit vector theta at right angles to the vector r, which will have components that you can figure out just from geometry. For instance, that's 90, and so this angle up here will be 90 minus theta, and you can work through that to figure out that the vector at right angles of unit length is just minus sine of theta, cosine of theta. And when I say these are unit vectors, what I mean is that you square each of the vectors, say by dotting it with itself, you get 1, because cosine theta squared plus sine theta squared just gives you 1. So they are indeed unit length. Okay, so now that we know the two basic vectors of our plane polar coordinate system, we can now use these to figure out what h actually is, because we want an expression for dr by dt. So, for instance, since r is just given by the magnitude times by the unit vector, we can work out the derivative of r with respect to time just by differentiating this product, which we can do using the product rule, where you differentiate the first term times by the second, and then you add the second term times by the first one, differentiated. So, sorry, that should be, we differentiate the unit vector and then times by the first term undifferentiated. Right, but how do we get the derivative of a unit vector? Well, we can actually use this expression down here. So the derivative of the unit vector can just be written as the derivative with respect to time of cosine theta sine of theta, which we can just write using the chain rule as d theta by dt times by d over d theta of this column vector, cosine theta sine of theta. And remember that cos differentiates to minus sine and sine differentiates to cos, so this here will just be minus sine of theta cosine of theta, which, oh look, that looks a lot like the unit vector in the theta direction. So we've worked out that the derivative of the unit vector, r with respect to time, is just given by d theta by dt times by the unit vector in the theta direction. So we now have this part, and we can now substitute the first term and the second term, which is just equal to this, up into this expression. And so what we will get down at the bottom is that h is equal to r crossed with r unit vector dr by dt plus r times by d theta dt multiplied by the unit vector in the theta direction. Notice immediately though that the first term will die because we've got the cross product of two vectors in the same direction. The second term will be fine though. We'll get h being equal to r times by d theta by dt times by r crossed with theta in the unit direction. And we could actually peel out a unit of the magnitude of r from here to make this be a unit vector, and write this as r squared times by the unit vector in the direction r. And the reason why I've done this is because by definition of the cross product, r unit vector crossed with theta unit vector must be perpendicular to both of them, and hence stick out of the plane. And this just defines the vector h. But because these are unit vectors, this will then give the unit vector in the h direction. So at the end of the day, what we've figured out is that the vector h can just be written as r squared d theta by dt times by a unit vector in the h direction. Alternatively, this is the magnitude of the vector h. So h is just r squared d theta by dt. So if we have a way to get h, and we already know, say, r for instance, you could figure out how the angle varies as a function of time. Great, so this is our first key result. Now what we're going to try and do is continue using this coordinate system to figure out how to solve our initial equation which we derive from Newton's law of gravitation. Right, so this is the equation that fundamentally we're trying to solve. We've already made some good progress in that we know we orbit within a plane, and that we've also deduced that h is equal r squared d theta by dt. And in working out h, we've already made some headway towards evaluating the second derivative, in that we've figured out that the first derivative of r with respect to t is just given at the end of the day by dr by dt in the r direction plus r d theta by dt in the theta direction. So to get the second derivative, we just continue doing this with the product rule. We differentiate term by term the above expression, and so we'll get d2r magnitude by dt squared times by r. We then differentiate the second term here, multiplied by the first, dr by dt times by dr unit vector with respect to time. And then for this term, we just differentiate each of the three terms, term by term, multiplied by the two undifferentiated, using the product rule again. So we're going to get dr by dt times by d theta by dt in the theta direction, plus r d2 theta by dt squared in the theta direction, and the final term r d theta by dt times by the derivative of the theta unit vector. Now we have all the ingredients to work this out apart from this bit, but we can figure that out just from this expression, in that d theta unit vector with respect to time, again using the chain rule, is just d theta by dt times by d over d theta of this minus sine theta cos theta. And because sine differentiates to cos and cos differentiates to minus sine, this here just gives us, for this part, minus the r unit vector, because we have an extra minus sign out the front from this derivative relative to just the r unit vector itself. So this entire thing here is just equal to minus r unit vector d theta with respect to time, although that's not a unit vector, d theta. Right, let's simplify this somewhat horrendous expression slightly. So we also notice that we remember that the derivative of the r unit vector with respect to time is just given by d theta by dt in the theta direction. So let's collect our terms. In the r direction, we get d2r by dt squared, and then we get a minus r d theta by dt all squared. So this is just the second term here, multiplying these two d theta by dt's. And then all of the theta terms we also get as well, which at the end of the day, two of the terms will combine. And so we'll end up getting, in the theta direction, 2 times by dr dt multiplied by d theta by dt plus r times by the second derivative of theta with respect to time. So we're not actually going to be that interested in the theta expression. You can certainly use it to look at interesting effects like the Coriolis force, for instance, but it's going to turn out that actually all we need is the r component of this expression to figure out how planets are going to orbit. So let's put all this together back into our original equation way up at the top and figure out what this is going to tell us. Okay, so here's what we've just figured out, all looking neat. And so what we can do, now that we have this expression for what the second derivative of the vector r is, we can substitute this expression into the equation that we're trying to solve just up here. And collecting the terms, we get that d2r by dt squared minus r d theta by dt all squared. And then I'm going to add this extra term here, which is also in the r direction, plus g times by the mass of the star plus the mass of the planet divided by r squared. All of this in the r direction, plus exactly what we have here in the theta direction, must equal 0. And because this is a vector equation, we require each of the components to be exactly 0. So this bracket here will equal 0, and also this bracket here will equal 0. And the key thing to note is that what we have in the square brackets there, an equation involving r, thetas and time, doesn't involve vectors anymore. We've actually reduced the problem to a second order differential equation involving scalars, which will be much more ready to solve. And we can also use the relation, which we figured out before, if you want to eliminate the theta, that h is equal to r squared d theta by dt, to see that d theta by dt squared, which we would rather not be in our equation, is just going to be equal to h squared divided by r to the power 4. I've just divided by r squared here and then squared the resulting expression. So if we substitute this into this expression, we'll get an equation just involving r as a function of time. So we have d2r by dt squared, where this r is no longer a vector, it's just the distance between the planet and the star, which is what ultimately we're interested in solving. So we have this minus h squared over r to the power 3. We had one r up here which cancelled with one of the r's down here, plus g times by the mass of the star plus the mass of the planet, all divided by r squared, is equal to 0. Solving this equation as it is in its current form as a function of time turns out not really to be something we can do, so in order to solve it we're going to make a unit transformation to solve for r as a function of the angle theta. Specifically, what we're going to do is define a new variable u as being equal to 1 over r, such that r is just 1 divided by u. And in terms of this new variable, we'll have that dr by dt is just equal via the chain rule as dr by du times by du by dt. And what is dr by du? Well, we can figure it out from this expression here, just by differentiating this with respect to time, with respect to u. We get dr by du is equal minus 1 divided by u squared. So this could then just be written as, say, minus r squared times by du by dt. And then du by dt itself can just be written as du by d theta times by d theta by dt. Okay, and recall also that h is equal to r squared d theta by dt. So we can actually eliminate d theta by dt over here and replace this just with h divided by r squared. And so this is just equal to minus h times by du by d theta. And so then we can get the second derivative of r with respect to time, d2r by dt squared. We just differentiate that once more and we're going to get minus h times by d over dt of du by d theta. And again, we can use the chain rule and we're going to get minus h d theta by dt times by d2u by d theta squared. And let's eliminate this d theta t again with a h over r squared. So all of this is just going to be equal to minus h squared, and 1 over r squared is just u squared. So we get minus h squared u squared times by d2u by d theta squared. So we can use this over here in order to eliminate this up here at the top. So if we do all of this, and also say we can replace this r cubed with, well, 1 over r cubed with u cubed on the top, same with the r squared over here. At the end of the day, what we'll get is that d2u by d theta squared plus u is just going to be equal to g times by the mass of the star plus the mass of the planet, and then that expression is just divided by h squared. So I've just taken that factor of g times the mass of the star, etc., over to the right-hand side. And so, crucially, this expression here for u as a function of theta can actually be solved. So let's go ahead and solve this, and the idea being that once we know what u as a function of theta is, we can get r just by 1 overing it, working out the reciprocal. Okay, so we're nearly there now. We have a relatively simple second order differential equation to solve. And so what we need effectively is some function u that when we differentiate it twice and then add it to itself, we get a constant. So I can immediately think of two functions that would do that. So if u of theta was equal something times by sine of theta plus a constant, then when you differentiate sine twice, so d2u by d theta squared, the first time you get cosine, the second time you get minus sine, and the constant dies, so you would get minus a times by sine of theta. And so you can see that when you add this to the second derivative, you would just get a constant, which is what we have on the right-hand side. So this expression would do it, and likewise, if you had an expression involving, say, cosine of theta, that would also do it. And we can generally combine these two expressions together using a little trig identity in order to get that the general solution to this equation would be u of theta is equal to some constant, let's call it alpha, times by cosine of the angle theta minus a reference angle omega, just a constant at this point, and then the constant we have to add is what we have on the right hand side here, g times the mass of the star plus the mass of the planet, all of this divided by h squared. And you can verify that this is the solution relatively straightforwardly just by plugging it into the differential equation at the top and just differentiating it twice and then adding it, which will make this term vanish, and you'll just be left with this. So the question now is there a slightly neater way that we can write this? And, well, how about we say take out a factor of, well, g times the mass of the star plus mass of the planet over h squared, and rewrite this as g times by the mass of the star plus the mass of the planet, all of this divided by h squared. So since we took out this factor here, we're just going to get a 1. And then what I'm going to define, since this is just an arbitrary constant alpha, I will say that alpha divided by all of this stuff here is just another constant that I'll call e. And then we get the cosine of theta minus omega. So all I've done here is just redefined constants, so I can write it as g times by the mass of the star plus the mass of the planet over h squared times by a constant e is what I defined to be equal to alpha. So now that we have what u is equal to, it's time for the moment of truth. So we know that u is g times the mass of the star plus the mass of the planet divided by h squared multiplied by 1 plus e cosine of theta minus omega. And this, I mean, sometimes people define this theta minus omega to be an angle called the true anomaly, and it's useful in exoplanets, but for our purposes here, we're going to define the reference direction omega to be equal to 0, which just means that we define our reference to be along the periapse direction. But don't worry about that for the moment. But we're interested in r, how the distance between the planet and the star varies as a function of the angle. And since r is just 1 divided by u, we therefore have that r as a function of theta is just given by h squared divided by g times by the mass of the star plus the mass of the planet times by 1 divided by 1 plus e cosine of theta. So we're practically there now. We can just use one more result in order to simplify this slightly. In that, remember that for the equation of an ellipse, what we were looking at earlier, we had say that the distance to periapse is given by a times by 1 minus e, and that periapse occurred when theta is equal to 0. So if you remember the diagram, it looked a little like this. Here is the star, here is the planet. This is the angle theta, this is r. So when theta is equal to 0, you're at your periapse position. And in fact, the equation in this form here is already the equation of an ellipse. So long as this constant down here, e, is between 0 and 1, this mathematically is just the equation of an ellipse. So if we plug in theta is equal to 0, in which case, recall that when theta is 0, cosine of theta is equal to 1, then what we'll find is that a times by 1 minus e is equal to h squared over g times the mass of the star plus the mass of the planet times by 1 divided by 1 plus e. We can then say multiply by this and multiply by this to get that h squared is just going to be a times by 1 minus e squared times by g, and this mass of the star plus the mass of the planet. So now that we know an expression for h squared in terms of the semi-major axis, we can write what our final result is going to be for the equation of a planetary orbit. So putting everything together, we finally have that the distance between the planet and the star is given by the semi-major axis A times by 1 minus the eccentricity squared, all of this divided by 1 plus e cosine of theta. And if you plot what r looks like as a function of theta, then you find an elliptical orbit exactly as Kepler deduced all those years ago. Well, that's all we have time for here today. Next time, I will be doing the much simpler, you'll be pleased to hear, task of deriving Kepler's second and third laws of planetary motion. Please let me know down below what you thought about this somewhat experimental video, and I hope you didn't get lost too much in the technical details. But thanks for watching, and bye for now. I hope you enjoyed this video, which is laying the groundwork for a new series on the science of exoplanets that I'll be producing later in the year. This week's feature video is an examination of the scientific objectives and instruments on board the European Space Agency's ExoMars 2016 mission, which successfully launched earlier this week. Next time, I'll be concluding our tour of Keplers Laws and be looking at some applications of them in astrophysics. Feel free to subscribe so that you don't miss it, and if you do have any questions or comments about this video, then by all means drop them down below and I'll be happy to answer.